In this video, we'll talk about LU factorization. This is a technique to increase the efficiency of Gauss elimination for certain applications. After studying this video, you should be able to perform an LU factorization on a matrix. And when I say that, do it by hand to make sure that you understand how it works. You should be able to identify when LU factorization is useful and why it's useful in those cases. You should also be able to implement LU factorization in MATLAB to solve a linear system, and explain conceptually how MATLAB left division works. So, what is LU factorization? LU factorization factors the matrix A, the coefficient matrix for a linear system. So still in that context of a linear system, AX equals B. A is factored into a lower triangular matrix L and an upper triangular matrix U. So before we talk about why it's useful, let's go through how that works. So here we have a matrix A expressed as a product of L times U. So let's go through and see how these are related. So we can write, just by implementing the definition of matrix multiplication, we can say A11 is equal to 1 times U11, and then we see zeros as we go down the rest of that column, so that's it. A12 is equal to, and again we'll go 0 times U11 plus 1 times U12 plus again 0 times plus 0. So A12 is equal to U12. And similarly, doing the same thing, you will find that A13 equals U13. So these three elements in the upper triangular matrix are the same as these three elements in the lower triangular matrix. Or sorry, in the original matrix A. So let's move down and work through the next row. So we get A21 is equal to, now we're in the second row, first column, so it'll be L21 times U11 plus 1 times 0 plus 0. And let's go ahead and do A31 next. A31, that will equal L31 times U11 plus L32 times 0 plus 0. So we see here, if we go through, U11, I'm sorry, recall that U11 is equal to A11, and so we can rewrite this as solving for L21. L21 is equal to A21 over A11, and similarly L31 is equal to A31 over A11. And if you recall from Gauss elimination, these are the elimination factors that we would be using in the forward elimination step of Gauss elimination. And we can actually use that to develop our technique to compute an LU factorization. And it turns out that that is also the case for L32. So the end result is L21, L31, and L32. Those are our elimination factors as we reduce the rows under the pivot elements U11 and U22. So the pivot elements were A11 and A22. So before we get into more how to do this and do an example with numbers, let's talk about why we do it. So many problems in engineering and numerical methods involve the solution of a system of equations for multiple right-hand side vectors. So this is a case where we might have the same coefficient matrix, but have the system AX equals some B1, AX equals some B2, all the way to some n different right-hand side vectors. Example situations would include calculating a matrix inverse, where to calculate the inverse of A, we can successfully solve for each column is going to be AX equals B, where B is equal to 1, 0, 0. That'll give us the first column of A. It's equal to 0, 1, 0. That'll give us the second column of A. So we'll call that B1, B2. B3 is equal to 0, 0, 1. Gives us the third column of A, and each of those corresponding X values build that, that inverse, A minus 1. Now we're not going to do much calculating of matrix inverses in this class, but I just wanted to point that out as an example situation. You can imagine calculating the inverse of a 100 by 100 matrix. All of a sudden we have 100 different right-hand side B vectors. Also, parametric analysis of a linear system. We'll be looking at that in a programming assignment. And down the road in this class, we'll see how several differential equation algorithms can include multiple solutions of the same linear system, with the only thing changing being the right-hand side vector. So recall that the computational cost of Gaussian elimination is concentrated in the forward elimination step. And in that previous video, we saw that that was order n cubed. That back substitution step was only order n squared. And what LU factorization does for us is it separates the time-consuming elimination step from the manipulations of the right-hand side vector B. So once we factor A, and as we saw, that is an elimination operation to factor A. So that factorization is going to be order n cubed operations, but we only have to do it once. Then we can solve for multiple right-hand side vectors using now two triangular matrices, and that's a substitution process only. So that's order n squared. So we'll look more into that in a minute, but first let's do an example of doing that LU factorization. So here's a matrix A, and what I will do is set this up as follows. So I'm going to write this as the product of two matrices, and I'll start by just having the identity matrix multiplied by A. So we know that this is true because a matrix multiplied by the identity matrix is equal to itself. And then I'm just going to start doing forward elimination on A, which is that right-hand side matrix. So we'll start under the pivot element 4, and we know that we could write row 2 is equal to row 2 minus, and then our elimination factor would be -2 over 4 times row 1. And then that elimination factor, as we talked about a few minutes ago, is going to be the element here, L21. So if we write that result, again, our first row is going to be unchanged. So we have 1, 0, 0, 4, 3, -1. And then we'll put the -1/2 here. And then going through and executing the rest of the eliminations, the subtractions here, we end up with -2.5. I'm sorry, that's still our lower triangular matrix. So this is still 1, 0. And then we've eliminated the first element under the pivot, and negative 2.5 and 4.5 is what we have left. Next, we'll go to row 3, and we get row 3 is equal to row 3 minus, and our elimination factor in this case is going to be 1/4 times row 1. So we'll go ahead and put that elimination factor there. That's again L31. So that goes into our lower triangular matrix, and the rest of that lower triangular matrix is as follows: the 0 and the 1. We've now completed our operations under the first pivot, and the right upper triangular matrix, we have a 0 because we've eliminated that element, and then 1.25 and 6.25, again carrying out that operation. So all that's left now is to move down to the next pivot, the negative 2.5. Doing that, we still have our second row is done. There's our 1/4. We're going to have another elimination factor to come in. And this is 4, 3, minus 1, 0, negative 2.5, 4.5, 0, and then our elimination factor now will be row 3 is equal to row 3 minus, and this is going to be 1.25 divided by negative 2.5 times row 2, and again that's just a negative 1/2. So negative 1/2, and sorry, that's still a 1 on the diagonal. So there's our lower triangular matrix, and going through those subtractions, we get a 0 under the pivot element and an 8.5, which is what's left. So there's our LU factorization. That is our lower triangular matrix L and our upper triangular matrix U. So then let's look at how we would use this LU factorization to solve a linear system. So here's our linear system, AX equals B, and we'll do that one factorization of A, and again that's going to be n cubed, approximately n cubed operations. And so we factor it into L and U, and so now we have LU times X is equal to B. And the way that we're going to solve this is we'll solve the intermediate system if we write this as UX is equal to D. So we get this intermediate system UX equals D, and this is an upper triangular matrix. So that upper triangular matrix now, and then we have a lower triangular matrix LD equals B. So each of these triangular matrices we can solve with substitution only. So in order to do that, we first, before we can solve for X, we need to solve for D. So the first system that we solve will be LD equals B. So we do forward substitution in L to solve for D, and that's going to be order n squared because it's a substitution algorithm only. Now that we have D, we can bring that over here and use back substitution in U to solve for X, and again it's order n squared. So the bottom line is we've done the factorization once, and then we can solve for as many right-hand side vectors, B vectors, as we want using substitution only. So recall one of the things about Gauss elimination, though, is that we might have had to do some partial pivoting to avoid problems of 0 or near 0 as a pivot element. And to keep track of that, now that we've decoupled the right-hand side from the left-hand side, we need to keep track of any partial pivoting that we do. So in order to do that, we use what's called a permutation matrix. And the permutation matrix, again, is going to basically keep track of the row shifts that we do when we're doing partial pivoting on the matrix A during Gauss elimination. So we would actually do the partial pivoting during the LU factorization. Okay, so this partial pivoting now, we're still going to do it, but now it's during the factorization. which recall is basically just a Gauss elimination process where we keep track of the elimination factors. And so then we can apply the permutation matrix as follows. So we would replace our linear system by multiplying both sides by p. So p times ax is equal to p times b. And our LU factorization would be of the matrix PA. And all PA is doing is mathematically implementing those pivots. And then we'll solve the system LUX equals P times B. So test yourself to make sure you understand how this is working. You can try out multiply P times some generic vector X. Here's an example P, and you should see that this permutation matrix would switch rows 1 and 2. So let's look at how you keep track of all this implementing it in MATLAB. You can do an LU factorization in MATLAB with the built-in function LU. It has the permutation matrix as an optional third output, but it in general is a good idea to use it. So here's an example solving the same linear system A for two different right-hand side vectors, two B's. So we'll do the factorization once, and remember, you're defeating the point if you do the factorization for every different B vector. So this affects how you write code using LU factorization. You might be looping through a number of B factors. You want to make sure you're not also computing the LU factorization with each iteration of that loop. So we do one factorization and then solve for our first D1, and again there's that permutation matrix which we need to keep track of any row shifts in B. Then we can solve for X1. Second time, solve for D2, again with the permutation matrix to keep track of the row shifts for B, and then solve for X2. So you might be wondering, well, it seems like now we're having to do two processes to solve. How is this more efficient? Well, consider an example where we need to solve a 100 by 100 system for 50 different right-hand side vectors. So in the case where we do that without LU factorization, we're going to have, for every Gauss elimination operation, we're going to have 100 cube operations, approximately. So we have 100 cubed operations times 50 systems. That's going to be about 50 million flops. If we use LU factorization, then we're going to have those 100 cubed operations, but we're only going to do it once because we only have one factorization. Then for those additional systems, we'll have, for 50 right-hand side vectors, we have 100 squared. That's our order n squared substitution cost. But we have it twice because we have one for U and one for L. So we have to go for each of those triangular matrices. But we still have a huge savings because we end up with only 2 million flops. So this is a 96% reduction in the computational cost. And it just gets even greater if we're increasing the size of the system or if we're increasing the number of right-hand side vectors that we solve for. So the bottom line is whenever you are solving a system for multiple right-hand side vectors, it's a good idea to use LU factorization. So this is a good time to talk about how MATLAB left division works. It's actually a lot going on with this little operator here, more than meets the eye. We can also talk about why this is preferred to the matrix inverse. So MATLAB left division uses the following algorithm. It starts by checking if A is triangular. If it's triangular, it just can go right through with a substitution algorithm that has an operation cost approximately n squared. Next, it checks if A is a symmetric matrix. If it is, it uses what's called a Cholesky factorization, which we're not going to cover, but it takes advantage of the fact that A is symmetric and actually is another n squared calculation. Next, it checks if A can be transformed to be a triangular matrix, for example, by some pivoting. And if so, again, it's a substitution algorithm that's order n squared. Lastly, if A is square, MATLAB left division is Gauss elimination with partial pivoting. So the pivoting happens automatically. And like we saw before, that's going to be order n cubed. If A is not square, if it's an overdetermined matrix, left division actually implements a QR factorization, which is a least squares solution. And we're not going to get into the details of how that works, but what that least squares solution is it's going to minimize the squares of the residuals. Remember, there's no perfect solution if the matrix system is overdetermined, but we can find a best, we could call it a best fit solution, and something that minimizes the total residuals in our result. So this is why left division is preferred to the matrix inverse. As we talked about a little bit earlier in this video, the matrix inverse, first and foremost, is going to require the solution of the system for multiple right-hand side vectors. And those multiple right-hand side vectors in MATLAB's matrix inverse algorithm, it does use LU factorization to do that, but ultimately it has more computational cost than left division and does not go through and check to make sure that it can't take a more quick substitution approach or Cholesky factorization approach. So again, matrix left division, that's our preferred mode, preferred method for linear systems. And that concludes this video.